Thank you very much. Yeah, before I get into the math, I want to just say a couple of words with the goal of embarrassing Hélène. No, I want to express my sincere thanks to the organizers for inviting me to speak here, because it gave me the impetus to really delve into some parts of Hélène's work and get familiar with it, and it was a wonderful experience for me. And just as a hint of the breadth of Hélène's contributions to mathematics, I've been reading at least 5 or 6 of her papers on this subject, secondary characteristic classes. And they weren't even mentioned in this really long spiel on the conference website about all of Hélène's contributions. And they're really wonderful papers, and it's been a great experience for me. So thanks to Hélène and thanks to the organizers. So I want to start with an introduction to secondary Chern classes. And towards the end, I hope to address some questions that Hélène raised in one of her survey articles. But my real goal is to just set the stage a bit and get everybody comfortable with this subject. So the setup is going to be that we have so V is going to be a complex local system on a space S. Now, you might be asking right now, what is a space? And the answer is it's whatever you want it to be. Nothing. I promise, whatever you think space means, what I say will be true. Okay? Yeah. As long as you know how to define a local system on the finite frontier, I guarantee you that. Complex local system. Okay. Well, then in particular, this yields a topological vector bundle, a complex topological vector bundle over S. And this has its classical Chern classes. So CNV for every natural number n in the second cohomology of S. It's standard to take integer coefficients. Following Deligne, I'm going to introduce a slight twist. So this Zn is just, by definition, 2 pi I to the n times z. It's an abelian group, but it's just sitting inside the complex numbers, but it's that particular copy of z, so to speak. So you have those Chern classes, just like for any topological Chern classes, just like for any complex vector bundle, but there's something particular that happens when the vector bundle started life as a local system. So transition functions being locally constant as opposed to just continuous. Then what happens is that if you change coefficients and you map into H2NS with C coefficients, then these Chern classes go to 0. So that's a basic fact about complex local systems, and it can be proved in maybe several different ways. There's the Chern-Weil perspective, and there's another explanation was more arithmetic, was given by Grothendieck. And I will at some point say something more about both of these reasons why this happens, but that point will not be right now. So for now, just take it as a fact that the topological Chern classes are torsion, which is the essential content of this claim. Okay, but when this happens, then, well, if you think of the long exact sequence in cohomology associated to, this sheaf going into C, these are constant sheaves, but this going into C and then the quotient, well, that means that this Chern class lifts potentially non-canonically to a class in degree 2n minus 1 with coefficients in C mod Zn. Now, what the theory of secondary Chern classes does is it gives you a canonical lift of this topological Chern class along the boundary map. So it says that, in some sense, there's a really good reason why the Chern classes vanish. So there's a canonical functorial lift along the boundary map. So the secondary Chern class is a functorial and canonical. Well, what does canonical mean? I don't know. So oftentimes it comes with a hat. H2n minus 1 S with C mod Zn coefficients. And now I guess maybe I want to take n bigger than 1 here, if in case you were thinking about a 0th Chern class. It's a bit of a different story there. Or bigger than or equal to 1, yeah. Okay, so...
So just a quick question. So this has nothing to do with tolerance, I mean, something like this, secondary.
Oh, no. Well, nothing to do. You never want to say that, but in principle, yeah.
It could be primary Chern class because it determines the other one.
That's actually a good perspective, yeah. So yeah, no. So what the key property of this is that it maps to the usual Chern class under the boundary map, the transgression or whatever you want to call it, associated to the short exact sequence, and it gives an explanation for why the Chern class has vanished there. Okay, so now what I want to do now is explain some facts about these secondary Chern. Well, one of the things I'm going to talk about is how there are actually two different definitions, at least two equivalence classes of definitions of this. So the question of whether this is a uniquely well-defined theory is one of the subjects of this talk, but what I'm going to do now, leaving that aside, I'm going to list some properties of these Chern classes, these secondary Chern classes, which will help you get a feel for them and which are known to be true for any possible definition you might give of these secondary Chern classes. Okay? So some properties. Right. So the first thing is you can look at the first Chern class. So classically, if you take the first Chern class of a vector bundle, it's the same as the first Chern class of the line bundle you get by taking the top exterior power. That's in H2 SZ1. And the same relation here persists to these more refined invariants. But now it's living in a more refined group, C mod Z1. But C mod Z1 via the exponential map is just C cross. And then the fact is, this class here is just, so this is just the Picard. This is exactly the thing that classifies local systems of rank 1 on your topological space S. And this is the isomorphism class of this line bundle. So in particular, for complex line bundles, this more refined characteristic class actually gives you complete information. It determines the isomorphism class of the complex local system. I'll put a warning here that you should be very wary of thinking that something analogous holds in for higher Chern classes and for more general vector bundles. It's very far from being the case. We'll talk about that a bit later. But still, it's an important fact. That's one thing. Another thing is showing that the theory has real content is some situation from manifold topology. So let me say, just to stick to the absolute simplest setting, so let's say M is a closed hyperbolic 3 manifold, and let me equip it with a spin structure. Well, this is for simplicity, basically. Then kind of say we have a uniformization by hyperbolic 3 space, and then the fundamental group acting by isometries on it. And this is essentially determined by the topological manifold, thanks to rigidity theorems, Mostow. And in particular, on M, you have a local system with values in the isometry group of hyperbolic 3 space, but that's just PSL2C. It's the same as PSL2C. And the spin structure lets you lift this to SL2C. So on any such manifold, we have a canonical 2-dimensional complex local system. And in particular, we can take its second Chern class, second secondary Chern class. So we can take C2 of this rho tilde, and that gives a class in degree 3 cohomology of M, and we can pair it with the fundamental class of the manifold. Did I say oriented? Well, maybe it, I don't know. Well, it's spin. I said spin. Good. Okay. Yeah. And then we just get an element in C mod 2 pi I squared Z. Okay. Now, 2 pi I squared z is 4 pi squared z. It's not a well-defined complex number, but its imaginary part is still a well-defined real number. And so the imaginary part of this was, let's see. This is, so there's some universal scalar, which is not like some obscure constant. It kind of just depends on how you normalize volume of the hyperbolic metric or something. But this is basically the volume of the three manifold with respect to the inherited hyperbolic metric. The imaginary part of this so-called Chern-Simons invariant. So it's definitely doing something interesting and non-trivial in this geometric example. Another situation you might look at is, so let me tell you something else about these secondary Chern classes, which relates to the reason why it doesn't matter what you mean by space is because there's a universal place, there's a universal S you can choose, which is an anima. Thanks, Lars. Right, yeah. So the universal ones live in B, GLN, C, and you have to really think of this as C with the discrete topology because we're looking at local systems where the transition functions, again, are locally constant. So it's like mapped to C with the discrete topology. So they live there, but you can pull back to something a little more, well, this is a crazy thing, but you can pull back to something a little more simple, so to speak, which is GLNZ. So you have a tautological complex local system living here. And now you can go from, say, a K group, let's say 2n minus 1, let me take n odd. And I look at K group 2n minus 1 of Z rationalized by some Hurevich. That maps to homology in degree 2n minus 1 of the infinite general linear group over the integers of rational coefficients. These just like the usual Chern classes, these refined Chern classes, they don't change when you direct sum a trivial bundle. So they all come from this thing. And then we can pair with the Chern-Simons, the Chern class of the universal bundle. And then we get something in C mod Zn. And then here n is odd, so if you want to get something well-defined, you should take the real part, but then you get a real number. And then, well, Borel showed that this is isomorphic to Q. This is a one-dimensional rational vector space. And he also showed, well, modulo maybe identifying some definitions of things. He also showed that the image of this Q in here, so the image is just, well, there's some power of pi, and then you have the zeta value, odd zeta value, zeta n times Q. So again, we're getting some very interesting numbers popping up from these secondary classes. In this case, odd zeta values are somehow being produced. Okay, so this is Borel. So this should tell you that this theory of secondary Chern classes is much more than just a refined explanation for why the Chern classes vanish rationally. It's actually producing you extra information with interesting numbers in various situations. Are there any questions about that?
Well, I think that the Grothendieck has bounds for Chern classes of the linear representation.
Yes, I will return to this.
Bounds should appear there.
I will return to this question. Yeah, I will return to this point. Yes?
What if you don't rationalize the Q?
Yeah, then I have to be more careful. I don't want to. Yeah, no thanks. Okay. So, right. So I'm telling you this is a wonderful theory, but you have to prove it exists. Well, wait, sorry. So how to produce these secondary Chern classes. So I then wrote this survey article, recent developments on characteristic classes of flat bundles, And she listed 4 methods for defining such classes. And then she said, I can show that 3 of them are equivalent. And then, so if you, if you partition the set of definitions into equivalence classes according to the equivalence relation of proven to be equal to each other, then you have 2 equivalence classes of possible definitions. And I will give you representatives for each equivalence class. Is this clear, what I've just said? Okay. So, so there are basically 2 ways. And the first way I'll say, this is not historical, but okay, is the method of Beilinson, and the second is the method of Cheeger-Simons. And maybe Chern, yeah. I don't know. I was reading the paper of Cheeger and Simons, but there was an earlier paper of Chern and Simons. So now let me, right, so let me describe these methods in turn. So I'll start with the method of Beilinson, which I find quite interesting. So it actually works in the setting of complex manifolds. But then how will you know something about a local system, complex local system on an arbitrary space and not just on a complex manifold? Well, you can actually generalize this to stacks. And then you plug in the stack, get ready, BGLN C with the discrete topology. It's a stack where like, it's a simplicial thing with discrete terms, yeah? But you could just view those discrete things as 0-dimensional complex manifolds. It's legal. So Beilinson does something here, but it actually extends to here, and then it specializes to here, and then that's going to magically give you the correct secondary Chern classes. I'm going to pause and let that strategy sink in for a second, because it's kind of strange.
So here you view the BGLN as an analytic?
Yeah, well, yeah, I would, but he said it was a simplicial set, therefore a simplicial complex for analytic space. Yeah. Has it sunk in? No.
But I have a question. Yeah. I mean, from what you said, why can't you just say, instead of setting of complex manifolds, just say setting of points?
Because there's a certain, well, when I say more, maybe it'll be clear. Yeah. So because there's something you can do with a complex manifold that you can't do with a point. I mean, well, you can do it with a point. Well, never mind. You'll see. Okay, so what can you do with a complex manifold? With complex manifolds, there is a more refined theory than just the usual topological cohomology, which is called Deligne cohomology. So.
You should talk on Beilinson. You should say Deligne Beilinson.
But it's not what's commonly known as Deligne. What I'm talking about is not what's commonly known as Deligne Beilinson cohomology. But I do prefer Beilinson's definition. I'm going to give Beilinson's definition of Deligne cohomology. Okay, so what do we have? There's the topological thing. So we have it's going to be a hypercohomology of some complex of sheaves, and we have the constant sheaf on this guy here as one part. But then we have the de Rham cohomology of your complex manifold, which this maps to just as the constants. And then we have a filtered piece of the de Rham cohomology here. So it's the same story as showed up in Lars's talk. And the Deligne complex is just the homotopy pullback. So this is Beilinson's definition of Deligne cohomology. And what's the point? Well, the first point is that if you look at the weight 1 Deligne complex, then it's just via again exponential map, you can trace things through. It's just a shift of C cross. And what this means is that you get tautologically, you get first Chern classes of line bundles in H2, then this -1 shift becomes a 1 shift of, whatever, with coefficients in Z1, Deligne. Okay, that's the first point, just by the definition, if you stare at the definition, you see there's a tautological way of defining the first Chern class. Now this is a line bundle in the sense of complex manifolds. It's not a local system anymore. It's a complex line bundle on a complex manifold. Has tautological first Chern class. And the second thing is that you have a projective bundle formula, which I won't spell out explicitly what it means, but you can understand the cohomology of a projective bundle just in terms of the first Chern class of the tautological line bundle via the usual procedure. And that explains why this particular choice with Fn and so on, it has to do with the cohomology of projective space, cohomology of differential forms on projective space.
Sorry.
Yeah.
I'm confused. So this, you also have ring structure.
Yeah. Yeah. Yeah, that's the point of writing it like that. Yeah, because I mean, this is a multiplicative filtration. Okay. If you take the direct sum over n, you get a ring structure on that. Yeah. Okay. So then you can use Grothendieck's method. You get a theory of Chern classes for complex vector bundles on complex manifolds or stacks with values in H2n with coefficients in Zn delene. Okay?
Sorry, when you say the complex vector bundle on complex manifolds, is that
holomorphic? Yeah. Yeah. Yeah, that's I was using the wrong term, so thanks for the comment. Yeah. Where was I going? Oh yeah, but note also that you could, if you put a 0 here, this is just a resolution of the constant sheaf C, holomorphic Poincaré lemma. And if you think about what that means, it means there's always a canonical map from C mod Zn shifted by -1 to this delene complex. And this map is an isomorphism for over spaces of dimension 0. So dimension 0 complex manifolds. Because in dimension 0, there's nothing going on with the de Rham complex. Sorry, for n bigger than 0. So if n's bigger than 0, then this term is 0, so you're seeing the same thing. But then it's also an isomorphism for BGLNC, the discrete topology. On that stack, this natural map is also an isomorphism. So when you specialize the theory of Chern classes for holomorphic vector bundles with values in delene cohomology to this stack built on this discrete group, well, you're producing these secondary Chern classes. By construction, or by comparison with the analogous definition of Chern classes in the topological setting, you're refining the topological Chern classes via this map here. Is this clear? Okay. But strange, right? Okay. Right. So now let me tell you about the method of Cheeger-Simons. Where was I? Oh yeah. Carlos, does that explain what you were asking? Oh, sorry, I didn't mean to distract you from your phone.
Yeah, I think so.
Yeah, never mind.
So I mean, at some point you have to use the fact that you can make your points into something bigger, right?
Yeah, you build projective bundles over the points. Yeah. Right. So okay, the second setting is the second method, the method of Cheeger-Simons for producing secondary characteristic classes. It works in a different setting. It works in the setting of C infinity real manifolds. So this is real manifolds. Now I can give, at this point, I can give the idea behind the Cheeger-Simons construction. It's because there is a good reason in the setting of real C-infinity manifolds why these topological Chern classes vanish when you go to complex coefficients. So the idea is, there's something called Chern-Weil theory. So if you have on a real C-infinity manifold, if you have a vector bundle and a connection, then you get to write down something called the Chern-Weil form, which is actually a closed 2n form on your manifold, which represents the Chern class in the de Rham cohomology. So this is a connection. Arbitrary connection, not necessarily a flat connection. But a complex local system gives you a vector bundle with a flat connection. And if you look at the construction of this Chern-Weil characteristic class, it's just a polynomial in the curvature, basically. So if the curvature vanishes, i.e. if the connection is flat, then this closed 2n form is identically 0. So certainly its class in cohomology is 0, but this, by the comparison isomorphism, this is the same thing as the topological cohomology with complex coefficients. And if you trace things through, that's proving the claim I made at the beginning of the lecture, in the setting of real manifolds at least. So the idea behind Cheeger-Simons, well, maybe, I don't know if this is how they actually came up. One way to motivate Cheeger-Simons is to say that this looks so canonical an explanation for why the Chern classes vanish that it must promote to a theory of secondary Chern classes. But to set it up, you kind of have to work in this world of arbitrary connections and not just flat connections. So the cleverest way to do this comes from a paper of Hélène's. So she said that the cleverest way to understand what Cheeger-Simons is doing is to use something like Deligne cohomology, but in the C-infinity setting instead. So we can also use a variant of Deligne cohomology. To explain this theory. So, but I'm going to differ from Hélène a little bit. So I'm going to call this ZND, and then I'll put this nabla here. And the way it's going to be different. Now I'm working on a C-infinity real manifold, okay? By the way, this should be a complex vector bundle on this C-infinity real manifold. So it's like a finitely generated projective module over the smooth functions with values in the complex numbers, if you want to think in terms of algebra. Okay.
Don't you have Chern-Weil theory for real?
You also have Chern-Weil theory for real vector bundles. So I'm just fixing the setting that I'm working in. Yeah. Okay, so variant of Deligne cohomology. So we're going to put the same Betty part, so to speak. So the same Zn. And then this again maps to the de Rham complex. Now this is the C-infinity de Rham complex. And instead of, now the usual Deligne cohomology would be Fn, and here instead I'm going to put F2n. And you might say, well, isn't this just Z2n Deligne? And I say no, because I put 2 pi I to the n here and not 2 pi I to the 2n. So I think this is better. I think it's best not to think of this as Z2n. Okay. Right, and then
Sorry, I've got a stupid question. Where does the nabla come in the rest of it?
It's notation.
It's just notation.
Yeah.
So there's no actual...
It doesn't depend on any nabla. It's just notation. And I'm glad that you give me the chance to clear that up. Yeah. Okay. So, all right. How am I doing on time? Yeah, fine. So there's a theorem of Cheeger-Simons. So there exists a unique functorial theory of characteristic classes for pairs, a vector bundle, and an arbitrary connection with values in H2n with coefficients in the Zn Deligne nabla, such that, so let me call, so I'll call it Cn hat V nabla again, such that, so we want it to be related to the conventional Chern-Weil forms. Now, if you take a look at this guy, and you remember that you're in degree n, and this is kind of in cohomological, well, yeah, so if you just project to this, if you project along this map, and you remember that you're in degree n, you realize that everything in here does give you a closed 2n form. And we want that this should go to the usual Chern-Weil form of V nabla. Okay? And let me say, and same for stacks. Again, this extends to stacks. Stacks based on smooth real manifolds. And then again, you can look at the stack BGLN C discrete, on which you have not just a vector bundle with connection, but a vector bundle with flat connection. And so this becomes 0, and you see that you lift to a characteristic class with values in C mod Zn. Okay. So I read a Len's paper, and I saw that there were these two definitions that weren't proved to be equivalent, and I thought this was extremely annoying. So I decided to prove they're equivalent. But let me say what's been done until now, as far as I can understand the state of the literature. So I'm doing bad board work now, but so there are, in the literature, there are many previous results giving comparisons between these two theories of secondary Chern classes, the Cheeger-Simons and the Bailenson. So comparison known in certain cases. So you can look, so it starts with Bloch, like unitary bundles on complex surfaces, and then it goes through, there's Gillet-Soulet, Berlinski. I think the latest paper is by Dupont, Hain, Zucker. And the upshot of this, as far as I can tell, is that the two theories agree for local systems on complex quasi-projective varieties. Which is nice, but it's a long way from, knowing they agree for general complex local systems. For example, the hyperbolic three-manifold case or something. I don't know. Yeah. So I don't know. So what I want to explain now, unless there are questions, of course, is how to prove that the two theories produce the same secondary characteristic classes in complete generality. So yeah, but if there are questions, yeah, Dan?
And maybe this is stupid, but why can't you just say, well, BGLN C delta is a simplicial thing whose objects are, in every degree is a discrete union of complex quasi-projective varieties to the town.
Oh, because that's not an argument. I don't know. They make, but actually, if you look in their paper, they make some comments about why their method doesn't extend to simplicial varieties. Yeah. So I didn't. Honestly, I wanted to take a different approach, so I didn't. Yeah. But they thought about it, and I trust them. Okay. Other questions?
So your approach comes down to that both of these previous theories generalize to stacks, and you use the CS as well.
Well, wait. I haven't told you anything about my approach. Why are you just guessing? I don't know. Why don't you let me explain instead?
Sort of being stupid. I mean, what's this map from that to close to forms?
Oh, it's just oh shoot! I erased the pullback square defining the Zn. But you know, there's the F2 end of de Rham cohomology here. So that complex of sheaves is just quasi-isomorphic to closed 2n forms sitting in degree minus 2n. Okay. Right. So what's the? I want to start with like I'm going to erase all 3 blackboards now. Sorry. In my opinion, the key to proving the comparison right. So in my opinion, the key is it's psychological. So don't be afraid to mix different categories or different kinds of geometry. So what do I mean by this? The issue with comparing these 2 definitions is that they take place in 2 different contexts. One is based on specializing something for complex manifolds. One is based on specializing something for C infinity real manifolds. One case you have a connection, in another case you don't. Okay. Yeah, you shouldn't be afraid to mix algebraic geometry, C infinity geometry, and complex geometry, and build things that have hybrid features. So what do I mean by that? Let me just give you a simple example so you see I'm not just talking some nonsense. So for example, let's say you have a C infinity manifold M, and then you have a vector bundle, no connection, V on M. Well, you can think about this algebraically as a finitely generated projective module over the ring of C infinity functions. So yeah. Well, I'm not going to distinguish between the vector bundle and its global sections. I apologize for that. No, well, yeah, compact, sure, yeah. Maybe, I mean, probably, what do you call it? Sequential union of compact is enough, but anyway, right, so then you have the algebraic vector bundle. So then you can view the total space in an algebraic way. So something like, so to speak, something like spec of sim over this ring of V dual. So I don't know, yeah, so you could also view the total space in a holomorphic way, in complex analytic way. So it's maybe as an underlying topological space, the usual total space, but now you're interested in functions on it which are like smooth families of holomorphic functions in the fibers. Yeah. You can also look at the associated projective bundle in C infinity or complex analytic or algebraic. So my point is that over a smooth manifold you can do smooth geometry, but you can also do complex analytic geometry, and you can also do algebraic geometry. This is well known, but not well absorbed, I feel. yeah, and you can also look at the associated vector projective bundle. Like you can look at the principal bundle that corresponds to this GLN torsor. You can look at it in any of several ways. Equip it with more or less structure. And so on and so forth. So, okay, so that's the background that what you need to open your mind to the possibility of doing. But what is it we actually are required to do in order to solve this problem? So what we need to do, we need to show that, so first of all, that Bailenson's definition works also and compatibly, works for C infinity manifolds. So giving a theory of Chern classes you can also write down the usual Deligne complex, not with F2, not with F2n, but just with Fn like before, but on a real C infinity manifold. So for arbitrary vector bundles without connection, and then we need to show that given a connection, we get a canonical lift to H2n m Z2nd. Oh no, not 2nd, sorry, ZND nabla. So this was just here we took the 2n stage of the Hodge filtration, there we took the n stage, but otherwise they're exactly the same. No, given a connection, arbitrary connection. This was where differential characters live here. Yeah, and then if you can do this, then you're done. Then it follows kind of formally by diagram chasing that the two different characteristic classes have to agree. Once you've explained that, so to speak, Bailenson's definition also works in the C infinity case and has this interaction with a connection, then the two things are compatible and you're okay. So the way I was formally framing this argument was in terms of the use the theory that Schultz and I have developed to address when in what settings or for what kind of analytic space you have a good theory of Deligne cohomology plus Chern classes. And I just found some axiomatic characterizations of when you have this, and I don't want to go into the details of it, but it applies in particular to smooth manifolds. But also, yeah, right. So in particular, for C infinity manifolds. I apologize that I don't have time to go into the, I was intending to present the axiomatics and so on, but in particular you have it for C infinity manifolds, and in a way that's manifestly compatible with the setting for complex manifolds because they're all in a general framework. So the key thing is to understand why in the presence of a connection, the characteristic class lifts to this to the 2n level of the Hodge filtration. So given a connection, need to lift. But note, recall the definitions. So here we had ZND nabla. It was Zn and then dram, and then F 2n dram. Whereas Zn without the d, which is where we currently have our theory, was the same except with just Fn. And then the map here is just including that into that. But if we want to lift something from here to here, this part is exactly the same for both of them. So it's enough to lift this thing to here. And And that, here we don't need any more Betty information, and we don't need any more Betty information to do that lifting problem. It's something, so to speak, purely algebraic involving the de Rham complex. So this reduces to a purely algebraic, well, this reduces to an algebraic. I'll put algebraic in quotation marks because you need to be doing algebra over a C-infinity manifold, but it's in essence purely algebraic problem. As long as you're doing algebra in some context where tensor products are completed tensor products and so on, which is what we built. So let me now give the key to doing this lifting. So algebraic problem with de Rham cohomology. So it's an idea of Cartan. So let's say we have M a C-infinity manifold and V a vector bundle. And then in particular we get a complex vector bundle, so we get a GLN C torsor on M. But we can, as I was trying to highlight before, we don't have to consider the GLN C torsor as a C-infinity manifold. We can consider it as something which is algebraic GLN C torsor relative to M. So in algebraic sense. So let's call this M tilde M. So this is, so over the base it's C-infinity, but on the fibers it's algebraic. And so that we have the algebraic GLN acting here and the quotient is M. Then, sorry?
GLNC is a complex Lie group.
No, it's as an algebraic group.
Okay.
Yeah. Right. So then there's the so-called Cartan model for equivariant de Rham cohomology, which usually you have to assume the group is compact for that, but that's just because they were working in the C-infinity setting. If you're working in the algebraic setting, you'd want to say it's reductive instead, and GLN is a reductive group. So if you do this thing here, then Cartan's model for equivariant cohomology works just fine. And what you get is that, so the Cartan's model says that via a very explicit map, you can look at differential forms on this mixed guy. If you just tensor it with sim of the Lie algebra of GLN and take G invariants, then you actually get a filtered quasi-isomorphism with respect to the appropriate filtration here. So sim G star G invariants map here, and this is the origin of Chern-Weil. These are the invariant polynomials that show up in Chern-Weil theory. So, and if you map this here, and then here, you find by the definition of the filtration here that you're landing in the nth filtration of the de Rham cohomology here, and you can check by looking in the universal case that this is indeed this, the characteristic class that you have here coming from the projective bundle formula and so on. So this composition describes the guy we have for an arbitrary vector bundle. Now what happens when you have a connection? When you have a connection, again, very explicitly, you get a splitting for this map of complexes. Yes?
So if the space of connection is a torsor on the omega-1 tensor on V, so you can write an extension of vector bundle,
yeah,
which is the space of all torsors.
Yeah.
And just picking just a connection is a section of that.
Yeah.
And I guess you can phrase that in terms of extension, an extension and splitting of these, taking into account that just a connection is a splitting of some canonical extension.
You're saying so there's some generalization of this story? Yeah, possibly. Yeah, that makes sense. Yeah, thanks. But the choice of a connection, so Cartan explained that given a connection, you get a map backwards, which inverts this quasi-isomorphism, but on the chain level. And if you follow through this and then this, you're exactly getting the construction of Chern-Weil forms. And in particular, it lifts it to the 2nth degree, just because this, all of a sudden, via this Cartan map, it's given by the curvature on this component, and it's just manifestly on the chain level lifting you to here. So, I mean, in the end, it's something very simple, but yeah, I thought it should be done. Okay. Any questions? Oh, sorry, Carlos had his hand up, and then is there a special? Yeah, but yeah, go ahead.
So are you saying this? You're talking about a manifold. So is this supposed to work in the simplicial case?
Yeah, that's a good question. In fact, it does, because everything is completely functorial and canonical on the chain level. Yeah. So there was one thing that wasn't, which was the claim that this construction here, inverting this quasi-isomorphism, agrees with the a priori construction via projective bundle formula of the characteristic classes here. But that you can actually check in the universal case by calculating what the filtered de Rham cohomology of the universal BGLN algebraic is. And there it's important that we made the remark that we have a purely algebraic problem here. And the reason behind that is some form of gaga, because by definition, this characteristic class used the projective bundle as a complex manifold, relative complex manifold, but by gaga, it's the same as if you consider it as an algebraic.
So is this solving the problem that Dupont, Haynes, and Zucker?
I assume it must be somewhere, but I have to say I didn't read their paper in such a detailed way. But yeah, I assume implicitly I'm solving the problem they ran into. Yeah. Other questions? Yeah.
What you do, you represent your Chern clause by some explicit co-cycle or extension, and you apply some push forward with respect to inclusion of Z into C, and trivialize that. And that, by abstract homological algebra, automatically produces a class in H to n minus 1. You see what I mean?
Well, yes.
It's just what you do when you're working with an explicit co-cycle representative. In some sense?
As I said, there are some parts of the argument that are very explicit chain level, and then there's one part more that's some that are more implicit, like with using gaga and using a calculation in the universal case for the algebraic GLN, BGLN. So it's maybe not as simple as that, but at least one part of it is like that, yeah.
Why did you say you use your theory with Peter to what you explain?
Well, I think you could probably say what I'm saying without it, but me, I used it because it seemed natural.
But where do you use it?
Well, because to have a language to discuss these sort of mixed objects and the de Rham complex on them, you see, it's a little strange what I'm doing, because if you think of a C infinity manifold, well, yeah, and Luc was kind of pointing this out when he said, oh, do you want M to be compact? And indeed, there's something going on there where it's not quite obvious how to consider that.
Because your theory is encoding the algebraic vertical direction
and the C infinity horizontal direction, yeah. And it's because we're working on affine, so really for a smooth manifold, we cover it by affines, so to speak, which are based on compact subsets of your smooth manifold and the rings of over-convergent smooth functions on those compact subsets. And on that level, you can do everything purely algebraically, whether it's smooth or algebraic GLN or whatever, in this category of C liquid, like liquid, this tensor category here. Everything purely algebraically, the formalism gives the usual smooth de Rham complex in one case, the algebraic de Rham complex in the other, and for the mixed things, it gives the appropriate thing, and so on. So there is, yeah. So for me, it was very convenient to use this theory. I'm not claiming that you have to, but I think the point of a theory is that it should make obvious things obvious. And well, I don't know. Yeah.
So which category does this M tilde live in exactly again?
It lives in our analytic stacks. Yeah.
Can you use cases?
No, unfortunately not, because you need to make sure you're getting the correct de Rham complex for the C infinity case. You need to know that the things like the famous tensor product theorem of Schwartz work with respect to the tensor product in the theory, and that's true for the liquid case, not for the gaseous case, for C infinity.
Sorry, I'm a bit confused. So this, what's the filtration on the right-hand side?
Yeah, so the filtration is the tensor product filtration of the de Rham filtration here, and the filtration on this symmetric algebra where this thing is kind of in degree 2, filter degree 2.
It's only G equivariant.
Yeah, G is acting just on, G is acting, so to speak, on both factors. Okay, I had a second thing in my abstract about arithmetic rigidity, and well, I find it interesting, and I don't have time to explain it, but...
So you have 5 minutes.
Yeah, well, okay, ooh. Best not. Thank you, though. Yeah.
You have to.
I will, but privately. Yeah. Yeah. Thank you for your attention. Yes.
So this is more of a comment, but I remember seeing these things with mixing the C infinity with holomorphic already in Kodara and Spencer and those type of people. Found it very confusing then. So it's nice to know that there's a straightforward.
There's a theory, yeah. I think we shouldn't be afraid of these things, yeah.
Also McPherson, I think.
Yeah, it happens all the time. Yeah, but.
Much earlier,
Yeah.
I think that Grothendieck liked the schema relative.
Yes, Hakim Grothendieck.
Yeah, so you were thinking of this sort of situation.
Yes.
Really.
Yeah.
Also, you promised to say something about the bounds.
Yeah.
And cyclotomic extension.
Yeah, so maybe I'll say very briefly that Corletta and Esnault proved a theorem which in particular, using Reznikov's methods, which in particular implies that if you have a variation of Hodge structures polarizable over a complex...
Can you say it again?
Oh, yeah, if you have V polarizable variation of Hodge structures over, complex, let's say a complex variety, smooth, I don't know. I mean, they prove something much stronger, but let me specialize it to this case. Then the Chern-Simons invariants are torsion, so these for n bigger than 1. And then they raised the question of whether you get, so in Grothendieck, as you mentioned, proved that you have a bound for, he proved something for the image under the boundary map, the usual topological Chern classes, that there's a specific integer that annihilates that thing, so a bound on the order of the torsion. And they asked whether you have the same bound on the level of Chern-Simons classes. And I can tell you that they do.
Oh, so it was in terms of the action of Galois on the of unity.
Yeah. This is a consequence of what I was calling arithmetic rigidity, which I don't have time to explain. But move it over to L-adic context and do something. I'll tell you.
Thank you. I'm glad to know it's correct.
Yeah. Yes?
There's this theorem of Davidson that his regulator agrees with Borel's regulator. Is this a special case of theorem?
Well, I don't know. Well, here, let me explain the situation. As far as I understand it, Beilinson proved that. Dupont and Hayne and Zucker proved the same statement for the Cheeger-Chern-Simons definition of the secondary characteristic classes. Now I've proved that those are the same, so yeah, that's right. So if you believe that Beilinson's explanation is simpler, then, well, I don't know. Did you understand what I was saying? Oh, so Beilinson said that with his definition, let me put a B of the secondary Chern classes. If you take the real or imaginary part, or whichever one you're supposed to, this is the Borel, gives the Borel regulator. And then Dupont, Hayne, Zucker, by a completely different argument, showed that if you take the Cheeger-Simons definition, and then you take the same thing, real or imaginary part or whatever, you get the Borel regulator. Now, I've shown that they're the same, so either you like Beilinson's argument, and then you say, oh, now I have a new argument for this, I go like this, and then like that, or you like their argument, and then you say, oh, I have a new argument for this, I go like this and like that.
Well, wasn't there a factor of 2 in there somewhere?
Yeah. There was, thank you.
Well, it's good you have 2 on both.
Yeah, they did both get 2. Yeah, Beilinson didn't have the 2, I think, and then it was fixed by Borel's.
My memory doesn't fail. First they had no 2.
Yeah.
So, it's good Carlos.
Are there any more questions? Maybe I have a question. So there is this sort of non-commutative counterpart this, which is the concurrency. I think it's known for thinking manifolds to be related. And can you also do this comparison?
Yes. So this was the approach of Karoubi that's mentioned in the Hélène survey article. And what Hélène writes is that with her method of modified splitting principle, she can prove it's equivalent to the method of the definition of balancing. So I refer you to the original source for further clarifications.
So if there are no more questions, let's